Hello, everyone. This is sequenced regular seminar time, and today we have a great pleasure to see Dr. Alexandros. How should I read? Papageorgiou, right?
Yeah, that's very good. Yes, very close.
Sorry.
Oh no, no worries. Yeah.
Okay, and the title of his talk is Rectifying No-hair Theorems in Gauss-Bonnet Theory. Please.
All right. Thank you for the introduction. I am a postdoc at the Institute for Basic Science, and I did my PhD at the University of Minnesota, and I did my bachelor's in Greece. And it is my very good pleasure to give you a presentation on our most recent work. This presentation is based on this paper that's highlighted in red, and it is a collaboration between Myok Park, Chan Park, and myself. So in general, my main area of expertise is cosmology and axion physics. So this is a new field for me. This is the first time I work on this. So it would be my pleasure to also give you another presentation in the future on axion physics if you're interested. And maybe I can even come in person. I think that would be better. Unfortunately, that wasn't possible this time. All right, so that's just to give you a bit of the backstory. This work started due to conversations that Myok Park and myself had on the issue of hairy black holes with scalar hair in particular. And after reviewing the literature, it became clear to us that the way in which people are dealing with these no-hair theorems, in which they're studying the evasion of these no-hair theorems is not quite correct. Instead, we wanted to write a paper to clarify the situation and express how we believe is the correct way to deal with these no-hair theorems for the Gauss-Bonnet theory in particular. And then we also recruited Chan Park, who is an expert on numerical relativity, because we wanted an expert to give us more confidence that our numerical work is correct and everything is fine. And we did exactly that. We wrote a paper, and I'm here to talk to you about it. All right. So this is the outline of my talk. I will spend the first 15 to 20 minutes introducing. I will make a brief overview of no-hair theorems and motivate studying the possible evasion of these no-hair theorems in modified theories of gravity. I will also talk a little bit about generalized theories of gravity, some motivation and some basic ideas. Then after the intro, I will do a brief overview of the, I think somebody has their microphone on. Myok? I think somebody has their microphone on. I can hear someone.
I think it's, yeah.
Sorry.
Yeah, please. Yeah, please.
Okay. Right. Excellent. So, yes, for the second part of my talk, I will make a brief overview of Einstein scalar Gauss-Bonnet theory. This is essentially Gauss-Bonnet theory with a scalar field coupling. I will explain how one performs the asymptotic expansions and how one ensures the regularity of the black hole solutions and so on. Then I will move on and I will explain the main part of this talk, which is how to establish the evasion or not of the old no-hair theorem. And then I will proceed to discuss the novel no-hair theorem, and I will discuss them separately. Finally, I will make some concluding remarks. Right. So let me now move on to the introduction. So general theory of relativity is the well-established theory of gravity. It is the theory that we use to understand the space-time geometry around massive objects such as black holes and so on. In general, GR is based on the Einstein field equations, and solutions of these Einstein field equations may describe the space-time on the external region of a black hole. One may impose the desired symmetry, such as spherical symmetry, axis symmetry, and so on, and may also choose some energy momentum tensor. And then one can explore in this way possible black hole solutions. It is really a remarkable fact of GR that there's really only 4 classes of solutions that are shown in this table. These are either charged black holes or uncharged, and rotating or non-rotating black holes. And it's really remarkable that all 4 of them there's an analytical derivation and they're known in closed form. And it's also remarkable that there's only 4 of them, even though in principle, a priori, one couldn't rule out the possibility of other possible black holes, perhaps black holes with lepton number or baryon number or color charge, and so on and so forth. So how do we know that these are really the only 4 possibilities in GR? We know that through what is called the no-hair theorems. So there's no one no-hair theorem. It's sort of a collective term for a number of theorems that taken together sort of ensure that black holes may be characterized only by these 3 numbers that I mentioned before: the mass, the electromagnetic charge, and the angular momentum of the black hole. And one of the motivations for studying these theorems in generalized theories of gravity is the pure mathematical one, to understand how robust are all these theorems that I just mentioned. One can ask, how robust are these theories? Do they always hold? Are they evaded under some circumstances? And what would it take to evade those theorems? And of course, in order to determine this, one has to study all the possible generalizations of gravity on a case-by-case basis and study the assumptions of these no-hair theorems and determine their validity or their evasion. So the pure mathematical perspective, I think, is one way of motivating such study. However, there's also the phenomenological reason to study the possible evasion of these no-hair theorems. Now, there's this possible phenomenology of deviations of GR black holes. This is a topic that deserves its own presentation, and I definitely don't know. I cannot exhaust this topic by myself. I'm just going to mention here one possibility, just because it's the latest one, the one that we became, that is basically a very recent development. 2 weeks ago, the Event Horizon Telescope announced the imaging of the supermassive black hole at the center of our galaxy. And then almost immediately, as an example, I picked this paper, which came out this week. People have already started to use this imaging to determine possible deviation from a Kerr type black hole. And in this paper, for example, they study how consistent this image is with modifications of gravity. And in fact, one of the possible modifications they investigate is the possibility of black holes with scalar hair, which is the type of hair that we will be looking for in this work. Our work is not this Lagrangian, it's a different model. However, it's still the same idea. It's black hole bestowed with scalar hair. And this is in fact what scalar hair means to us. It's essentially a black hole with a non-trivial scalar field profile in its external region. So, of course, in order to study the phenomenology of possible deviations from GR black holes, one needs to know the extent to which we can violate these no-hair theorems, and one needs to know the exact parameter space for every theory over which the no-hair theorems can be violated. Moving on, separately from the issue of the no-hair theories, of the no-hair theorems, it is also important to study the properties of generalized theories of gravity. It's only reasonable to ask the question of what happens beyond GR. This, of course, is some very, very generic generalization that I've written here, assuming that f is just some arbitrary function. And such Generalized theories of gravity may arise as lower energy effective theories from string theory, Lovelock effective theory in 4 dimensions, scalar tensor theories, Horndenski, and so on and so forth. Again, it's important to systematically organize these theories and study on a case-by-case basis what happens to the no-here theorems in these cases. Do they still hold, or are they evaded? And in particular, as shown in this very generic temple, I will only be interested in black holes with scalar hair for the purposes of this presentation. So let me give you a brief overview of the story from the 70s all the way to today. As far as black holes with scalar hair in particular. And we'll also focus in the most basic, simple type of black hole, which is a static and spherically symmetric and asymptotically black hole, asymptotically flat black hole. So the first no scalar hair theorem was derived by Bekenstein and Teitelbaum in 1972. I will be calling this theorem the old no-hair theorem. And it's based on studying the equation of motion and performing integration over the equation of motion and ensuring that the resulting integral is consistent in a sense. However, this theory has a loophole. It doesn't eliminate all possibility for hairy black holes. Instead, the loophole is that the theorem doesn't hold for negative potentials, for some Higgs-like potential. And initially in this theory, we're talking about pure GR. This is not some generalized theory of gravity. Soon afterwards, possible evasions of this theorem started appearing in the literature. We have the discovery of black holes with Schirmer hair and hairy black holes in conformally coupled scalar field, again by Bekenstein. And then in 1995, Bekenstein used a completely different approach without using the equation of motion for the scalar field, instead by studying the properties of the energy momentum tensor to derive what he called the novel no scalar hair theorem. And I will be calling this the novel no hair theorem for short. And in fact, this is a much more general theorem that covers a lot more theories than the old no hair theorem. And it also closes the loophole that I just mentioned before. It eliminates the possibility that there's hairy black holes, even for a negative potential, for a Higgs-like potential, and so on and so forth. Now, even the novel no-hair theorem was shown to be evaded, however, in cases when the scalar field is non-minimally coupled to gravity. And almost immediately the next year, it was proven that one can obtain dilatonic hairy black holes with a dilatonic coupling between the Gauss-Bonnet term and the scalar field. There's actually also a group at Sequest that has worked on this dilatonic coupling and evasion of no-hair theorems. And many other theories. I mean, this is definitely not an exhaustive list. There's many, many more. But what we're going to be focusing on is in particular the Einstein scalar Gauss-Bonnet term theory, which is a theory in which the Gauss-Bonnet term is coupled to the scalar field with some generic coupling, which we will not be specifying except for the purposes of the numerical work. And the first work that appeared that studies this more general theory was in 2017 by Antoniou, Caddy, and so on. Excuse me. So, as I mentioned at the very first slide, the evasion of no-hair theorems in Gauss-Bonnet theory with a scalar field was initially carried out in this paper by Antoniou, Bakopoulos, and Canty. We found that our results contradict their analysis in the case of the old no-hair theorem, and we find that their approach to the novel no-hair theorem is not complete. In fact, our approach sort of generalizes their results for the novel no-hair theorem. And I will explain in detail when the time comes what are the differences and so on and so forth. This is very important work because establishing the correct criteria for the evasion of no-hair theorems is very important for determining the robustness of the theorems. Okay, this should have said theorems, not theory. This is a typo. Sorry about that. And for guiding future phenomenological work, because understanding to what extent these non-Kerr theorems can be evaded is precisely what is going to tell us which parameter space is the one that we should be targeting for in comparing with future observations. So let me now move on to the main part of my talk. I will now give a brief overview of the properties of Einstein's scalar Gauss-Bonnet theory. I will derive the asymptotic expansions and so on. All right, so this is the model that we will be working with. G stands for the Gauss-Bonnet term, which is defined in equation number 4. It is quadratic in curvature, and F is some arbitrary coupling function, which will remain arbitrary for the purposes of the analysis of the theorem for the analytical part of our work, but which will be specified in the numerical part of our work. This is a very interesting theory because it has a number of attractive features. It is quadratic in curvature, and one expects that the next important corrections to Einstein's relativity will be quadratic in order. Another important fact about this theory is that it yields equations that are up to second order in the metric functions, and they all only contain up to second order derivatives in the equations of motion. And this implies that this theory doesn't suffer from Ostrogradsky system instabilities and so on and so forth. This theory is also topological in 4 dimensions. This theory also has good properties from the perspective of cosmology. One can construct cosmological models with this theory that are singularity free. And finally, particular realizations of this theory, particular coupling functions, they've already been studied, and it has been found that they can acquire hairy black hole solutions. So it's important, so it's interesting to generalize these cases to some arbitrary coupling F, for example, for Z2 symmetry and so on and so forth.
Excuse me?
Yes?
May I interrupt? Yeah.
Yes, please.
Do you allow this function f trivial, vanishing?
By vanishing, do you mean constant?
Just zero or constant, yeah. Constant is the Gauss-Bonnet is total derivative, so it did not affect the equation function. So just a trivial case, yeah. Because
yes. Sorry.
I'm saying this because even just check that for it, 1968 and 1948. There are rather well-known solution to this Einstein gravity coupled to massless scalar, which has 2 free parameters. Are you aware of that? These are obtained by Fisher, Yanis, Newman, yeah, rather well-known people.
Sorry, I didn't understand exactly what theory you're talking about. Do you mean that F is 0, so this is absent?
Yeah, then there are 2 parameter static, spherically symmetric solution.
Yes, I'm familiar with, I think, with what you're talking about. This would be just standard Einstein gravity and massless scalar field. That's what we're talking about.
And then the metric general spherical solution has 2 free parameters.
That's right. However, it's my understanding that these solutions that you're referring to are not finite. They're not regular solutions. They're non-regular solutions.
There is a naked singularity. Are you referring to that?
Yes, yes. What I'm referring to is that there's a naked singularity on the horizon. Yes.
Okay, so the no-hair theorem restricts on the absence of naked singularity.
That's right. Yes, we will be very explicit about that. We will demand that the horizon is regular. Yes.
Okay, thank you.
Thank you for the question. And yes, I should have said that at the beginning, but please do feel free to interrupt me at any point. All right. So variation with respect to the metric components lead to the generalized Einstein field equations. The left-hand side is the standard Einstein field equations. And on the right-hand side, we end up with a rather non-trivial expression for the energy momentum tensor. Notice that the energy momentum tensor itself depends on the curvature in this case, as well as the scalar field. And variation with respect to the scalar field yields the new equation of motion of the scalar field. And throughout this work, just to establish some notation, the dot represents derivative with respect to the scalar field phi. Next up, in order to continue our analysis, the next step is to assume some metric ansatz. This is one of the standard metric ansatzes that are being used in studies of fairy black holes. And according to this ansatz, in order for us to assume correctly that the existence of a horizon, A and B must vanish close to the horizon. So this is the schematically the type of expansion that we perform, asymptotic expansion that we perform close to the horizon. Epsilon is the difference between some distance r greater than rh minus the horizon radius, and epsilon is small. Exactly on the horizon, of course, epsilon is 0, and that ensures that both A and B are indeed 0 on the horizon, as they should be. In the case of the scalar field doesn't have to be 0 on the horizon. It is some constant plus some deviation from the constant that is proportional to this small parameter epsilon. This is essentially just the Taylor expansion around the horizon. Oops. Excuse me. Okay. Now, I don't want to write the equations of motion and overcomplicate things, because the equations of motion are very complicated in this model. But the bottom line is, if we enforce that both phi, the field phi, and its derivatives are finite on the horizon, which we want because we're exclusively interested in regular black hole solutions in this work, we end up with the first necessary constraint for the existence of regular black hole solutions, which is collectively given by these two conditions. In other words, only when these two conditions are satisfied can one ensure the regularity of the horizon, the finiteness of the energy momentum tensor, and so on and so forth. This is the first constraint on the coupling function f, because in order for everything to remain nice and finite and real in this equation, the quantity underneath the square root has to be positive or 0, which implies that this inequality must strictly be satisfied in order for the horizon to be regular. You might notice that I don't have the equal sign here. I only have the inequality, because the equal sign is further restricted in order to ensure that phi double dot remains finite. And that eliminates the equality essentially and leaves this as the only possibility. So we will only care about this part of the parameter space in terms of the relation of the coupling f and the horizon radius. Additionally, we expand the quadratic curvature invariant, and the reason why we do this is precisely what we were discussing before, because we want to ensure that our solutions will not involve a naked singularity. Instead, they will strictly represent a regular horizon. And one can see from this expansion, there's no possible way the right-hand side can diverge, except if we set the actual horizon size to 0, in which case, indeed, we get the naked singularity. So the bottom line here is that our theory admits a well-defined expansion around the horizon. It admits spherical symmetry, and the horizon is regular. We can do the same thing at infinity, but at infinity, as one might expect intuitively, the story is exactly the same as in the case of standard GR with the scalar field. There's no difference, because the Gauss-Bonnet term is quadratic in gravity, in curvature. So it is only relevant at the strong gravity limit. And it decays too quickly at infinity to make any difference. So as far as the expansion at asymptotic infinity, it's the same as just standard GR, and it is also well defined in this theory. By well-defined, I mean that one can specify these parameters, A1, Phi1, and find the constraints between them. And the point I was making is manifest in these two asymptotic expansions of the Gauss-Bonnet invariant. As you can see, it has some finite contribution on the horizon. This is finite plus something that's proportional to epsilon. However, its asymptotic expansion goes to 0 and it decays actually quite quickly as I to the 6th. The second takeaway is that it also admits a well-defined expansion at asymptotic infinity.
So question.
Mhm.
Right, so in the previous pages,
This page?
one more, please.
Mhm.
So,
Okay.
so near horizon expansion, what about the AH? Is it undetermined?
It is determined just for brevity, in order to save some space. I didn't write all of them explicitly. The point is that AH is fixed as long as we impose these two conditions. There are necessary relations between AH, phi H1, and BH. So as long as we specify these, AH is fixed, except for one constant, which is impossible to determine on the horizon. In order to determine this constant, one has to evaluate the solution at infinity. That happens because in the equations of motion, A always appears in ratios. For example, A prime divided by A or A double prime divided by A. So there will always be one undefined constant in AH.
So you mean that AH is proportional to BH?
Yes, exactly.
Yeah, up to some non-dimension factor at the horizon.
Yes, that is correct.
Okay, thank you.
All right, thank you for the question. Right, so let's now get into the main part of this presentation, and let's go over in detail how the Old-Noether theory, what form it takes for this particular theory. Right, so we're going to follow Bekenstein's footsteps, exactly the same process he did with his Old-Noether theorem. The starting point is the equation of motion of the scalar field. This is the expression inside the square brackets. We multiply the equation of motion by f in this case. Bekenstein multiplied this by the field itself, phi. But instead, we want to do something that we believe is more appropriate for this theory. We multiply by the function f of phi. And then we perform integration by parts on the first term. And we end up with the expression on the second line. The main point of disagreement between our work and the work of Antoniou and so on and so forth I showed you before is that as far as we are aware, everyone in the literature automatically disregarded the second term, disregarded the surface contribution, and assumed that it is 0 because it is 0 in Bekenstein's case. And then, of course, if the second term is 0, the only way that one can achieve the validity of this theory, of the validity of this condition, is to ensure that the parenthesis vanishes locally at every point in space, from the horizon all the way to infinity. The only possible way that this parenthesis can vanish is if the two terms have different signs. And since the first one is strictly positive, the second term, f times g, also has to be strictly positive. G is always positive, and therefore f has to be positive. And that was the conclusion that the paper I showed you reached, that f has to be positive in order for us to have a cancellation between these terms in the parentheses, and we can have 0 is equal to this integral. Our main claim is that this surface doesn't vanish, because the reason why this term vanishes in Bekenstein's Old-Noether theorems are no longer valid for this theory. And I will explain in more detail what I mean. So the angular integration and the time integrations are trivial, so we can perform them because of spherical symmetry. And one is left with equation 17, which is the previous condition, but just simplified somewhat. So let's investigate what happens to this surface term. As I showed in my expansions, phi admits a Taylor expansion at infinity, which means that this dr phi term drops as 1 over r squared. So we have a term that drops as 1 over r squared, but we also have, from the integration norm, a term that increases r squared, and the two contributions cancel. So whether this term overall vanishes at infinity or not, of course, GRR is 1 at infinity because of asymptotic flatness. Whether the surface term vanishes or not depends exclusively on what happens to the field, the function f. And I can, in fact, simplify what I just claimed. If you explicitly compute this surface term, you're left with this expression. So it depends on f evaluated at infinity times phi 1, which is this coefficient of the second term in the expansion at asymptotic infinity. And of course, phi 1 is deeply related to the scalar charge, which is just some definition for the charge of the scalar field that is analogous to the case of the charge for electromagnetism. The main point is that if this surface term vanishes, then indeed the conclusion that the previous works reached are the correct conclusions. However, this term only vanishes if f of phi infinity is 0 or if phi 1 is 0. Then in that case, we can obtain hairy black holes only for positive f. If this surface term is non-zero, then the surface term doesn't vanish, and then as far as we can tell, through this approach, it's not possible to restrict the possibility of obtaining hairy black holes. And this is in contrast to Bekenstein's case, because in Bekenstein's case, he studies the case of massless and massive scalar fields separately. So one can imagine what happens in the standard Bekenstein's all-no-here theorem. You get the same surface term, only instead of f, you have phi, the field phi. In the case of a massive scalar field, this surface term does vanish because a massive scalar field does not admit this Taylor expansion. Instead, it decays in some Yukawa-like manner. One can expect that also intuitively by taking the for analogy electromagnetism, because for a massless gauge boson, you have this 1 over r decay, but if you add the mass to the gauge boson, you have some Yukawa-like decay. So something similar happens to the scalar field. So because the decay is exponential, the exponential decay in the massive case dominates over the polynomial increase. And that is why in Bekenstein's case, he was, of course, correct in eliminating this surface term. In the massless case, something interesting happens in Bekenstein's case. There's a shift symmetry, which means that this phi, that would be here in Bekenstein's case, is unphysical. So for physically relevant configurations, I can subtract any constant I want, and I can subtract phi infinity out. Phi infinity plays no role in the theory. So then again, the surface term indeed vanishes, and then the only thing that's left in the integral is the kinetic term. And if the kinetic term is forced to be 0, that eliminates the possibility of having non-trivial scalar hair. For this theory, though, neither of these arguments hold. We do not have shift symmetry because this is some arbitrary coupling f. It doesn't have to be a shift symmetric coupling. And at the same time, this is a massless scalar field. So neither of these arguments hold, and that is the reason why the surface term has to be there. And to our knowledge, this surface term contribution has been neglected in previous analyses. And as you will see in the numerical component, we have been able to show definitively that the surface term is there, it's important. And this also justifies why one may obtain hairy black hole solutions for negative F, which normally is hard to see in the analysis that happened before. In particular, this is of particular importance because for the dilatonic coupling, which is one of the couplings we'll study in this work, it is actually impossible to satisfy this condition. The only possible way in the dilatonic case, F could be 0, is if phi of infinity became infinity, if it diverges. But if it diverges, that ensures that the energy momentum would diverge, and therefore we wouldn't have regular black holes. So actually in the dilatonic case, as you will see later, it is actually never the case that the surface term vanishes. So just to initiate the numerical part of this work, I want to establish some notation. Beta is a parameter that is essentially analogous to phi dot. It is a rescaling of phi dot, but it is helpful to define beta because beta strictly ranges between -1 and 1. So by using beta as a parameter.
Excuse me?
Yes.
There is a question in the chat box. Yeah, please,
Oh,
please,
okay.
please check it.
I didn't see it. Sorry. Chat box. Okay, sorry. It's in the other screen. Have we checked our analysis for the paper? Okay. Yeah. Yes. I took a look at this paper indeed, and but not in enough detail to be quantitative or anything. I do not know if we agree on the numerics, but it is my understanding that even in that paper, when the old Noether theorem was studied in this way, the surface term was disregarded incorrectly. However, the authors of this paper study the old Noether theorem in a different way by multiplying by a different function, and in that case, it's possible that no surface term arises. So I don't know about the second formulation, that I haven't checked in detail. Does that answer the question, or? Right. I guess to clarify a little bit more, that paper studies the old Noether theorem in this way. That was the original way in which this 2017 paper studied, and they also ignore the surface term, and we believe this is incorrect. However, it also studies the old Noether theorem by multiplying with a different function, and then we have not made that analysis. We cannot claim whether we're in agreement with that that type of analysis or not.
So yeah, actually, yeah, I have a comment.
Yeah,
Sure.
I guess that if you, in your constraint integral equations, if you take the f function as a different one, especially exponential f, then you could extract the f in front of the g. Then regardless of the sign of the f, you could make the integral constraint equation. So it's a different way. So we have analyzed about that in our paper, but unfortunately, the papers does not cite it in your one. So yeah, I'm just asking about that. Thank you.
Okay. Can you repeat the modification if we take what on the left-hand side?
Sorry?
Can you repeat what is the modification that you mentioned?
So I mean that in equation 15 in your presentation 5, if you take the f outside of the rectangular bracket, if you take the exponential f instead of the f, then you could extract the f in front of the g in equation 16.
Okay.
Square root round mu phi minus g. So here is f could be extracted from the round bracket. Then you could get the constraint integral equation regardless of the sign of the f.
Okay.
Function of the f. You
I
take the whole f.
Mhm. Okay, I agree with that statement. However, the question,
Yeah.
I don't think we disagree on what happens inside the integral. I agree that, okay, we can do a different manipulation with what we multiply. The question is what happens at the surface term though, if we do make that choice? Does the surface term vanish or is the surface term finite in this case?
It's a good analysis. And if you apply that the later part, the boundary term in our analysis, even in that case, the f could be extracted from the round bracket in equation 16. So I mean that regardless of the form of the f or sign of the f, you could make the constraint integral equation.
I guess what I am not so sure we agree on is that making such an integral constraint is only meaningful as long as the surface term goes to zero. It's
that
infinity.
is good. That is good.
Okay.
Yeah, that's good.
If one cannot guarantee that, there's no meaning in any constraint, right? This doesn't have to be zero necessarily. So
that's right.
Okay, that's the point. Yeah. But other than that, this manipulation, I agree that it's good in the sense that, okay, it eliminates that problem. That if you do manage to make the surface term zero, then indeed you don't have to worry about f because it's not present here. Yes. Right. Miyuk, did you have a comment? Sorry.
Okay, so I'll comment later. So yeah, please keep going.
Okay, good. Right. So as far as the numerics are concerned, we define this beta that, as I said, is equivalent to phi dot, but rescale, so that it ranges from -1 to +1. And beta, we're using a convention in which beta is always assigned the same sign as alpha, which alpha is the sign of the coupling. It's the parameter that characterizes the strength of the coupling. I just realized that I didn't define alpha so far. This is my mistake, but yeah, it's alpha should be understood to be the strength of the coupling, the prefactor of the coupling, and controls the magnitude and the sign of the coupling. Right, we fix the size of the horizon to be 1 throughout, and we vary the field value on the horizon. We solve the equations of motion and we fix the boundary conditions by the well-defined expansions that I showed a few slides before. So all three of us did independent numerical work, and we did this both with Mathematica and Python, and we all found the same results. So we're quite confident that, at least as far as the numerics are concerned, our work is correct. And this is the main results. So what you can see here is phi infinity in the top left panel, defined by the value of the field on the horizon. If this ratio is 1, that essentially means that we are in the trivial scalar field case, because there's no variation in the scalar field. And this only happens if the coupling vanishes. So when beta is 0, that is equivalent to saying that there's no coupling, that alpha is 0. And sorry, I should have said this is for the dilatonic coupling. So we fix gamma to be equal to 1 and vary phi and beta, where phi, we vary the field value, and beta is equivalent to varying alpha. And we scan both negative and positive betas, and therefore we scan both negative and positive alphas. So at the very center of these solutions, we have the value 1, which is expected because in the absence of coupling, we have to get trivial scalar hair. We already know that from Bekenstein. So it's good that our numerics show that. And then as you scan the parameter space, you end up with different ratios between phi infinity and phi h. In the top right panel, we single out one particular value of phi h. All the panels will be for phi h is equal to 0.1. And I show various different solutions for different choices of beta. And on the bottom left panel, we demonstrate what happens to the bulk and surface term. So we compute the bulk and surface terms independently. The bulk term is essentially the integral from the horizon all the way to infinity. And we compute the bulk term this way. the surface term is computed completely independently. The value of the field from the horizon doesn't matter. The only thing that matters is evaluating the field at infinity. And yet we find that they're exactly equal and opposite, which confirms our analysis that the surface term is not possible to neglect, but instead it is important and it has to be considered when studying these theorems. And the other thing that you can see in this plot is that, in fact, as I mentioned before, F can never be 0 for the dilatonic coupling. And hence, for the dilatonic coupling specifically, we never have a case in which the old Noether theorem is respected. And you can see that by the fact that the surface term never becomes 0. It only becomes 0 when there's no coupling at all, which we expect anyway. But as long as we have non-zero coupling, there is no possible way the surface term is not going to be there. And that is why there's no possible way to really restrict the hairy black hole solutions in the case of the dilatonic coupling. And just for reference, I've also included the charge. You can see that there's always a non-zero scalar charge, except for the case of absence of coupling. We did the same work for the Z2 symmetric coupling. Again, you can see different choices of values of phi on the horizon, and we varied beta. Just to make things a little bit faster, let's isolate our attention to the blue line only on the top left. We choose the value on the horizon to be 0.1, and then we vary the coupling strength, beta. You can see that at some point, there is a particular beta for which phi infinity can indeed be 0. This is expected because unlike the dilatonic coupling, there's no problem with phi. Phi can always be 0 at some point. For this particular value of beta, when phi becomes infinity, you can see that for this particular value of beta, indeed the surface term becomes 0. So the surface term becomes 0 in this case because f of phi infinity is 0. And that's why we see both the bulk and surface terms become 0 in this case. However, an interesting and peculiar fact is that both the bulk and surface terms again become 0, even though phi infinity isn't 0 for this particular value of in the parameter space. So the reason why we get a second 0 of the bulk and surface terms is that the charge becomes 0 for this particular value. And if the charge becomes 0, that means that we're satisfying the second condition for eliminating the surface term. So instead of having f of phi infinity become 0, we have the expansion constant phi 1 becomes 0 in this case. Of course, the vanishing of the bulk and surface terms can only be achieved for positive beta, which is something that is consistent with our analysis. Because in our analysis, we showed that the Noether theorem would hold if beta was negative, and at the same time, the bulk and surface terms vanished. But since we're finding hairy black hole solutions all the way to -1, that ensures that the bulk and surface terms can never become 0. And the fact that they grow indefinitely for negative beta is just a reflection of the fact that the Noether theorem holds for vanishing surface term and negative couplings. So all of our numerical results are consistent with the analysis of the old Noether theorem.
Question.
Yes.
So in the phi of R plot, yeah. So the left hand endpoint is maybe the horizon, right?
That's right.
Yeah. What about the inside of the horizon? So you cannot interpolate the solution into inside the horizon.
As far as I'm aware, we just didn't attempt to do that. At least I didn't try to do that. I don't know if my colleagues did. We never discussed about the extrapolation in the interior of the black hole, and I did not attempt to do that. So
Yeah,
I don't know what happens.
I also didn't try though, and I don't know how to we can extend it to the inside of the black holes.
See.
Yeah.
Anyway, in
Mhm.
this case, I think, do you have an inner horizon also, or just the outer horizon?
So yeah, actually, as I know, we are not sure if this case can have the inner horizons. We just carried out we just use the boundary condition, assuming the outer horizons and infinity asymptotic behavior.
But I think you haven't checked that the stability yet.
Actually, yeah, that would be the next project. Yeah.
Okay, I see. Thank you.
All right, thank you. All right, and now let's discuss the novel no-hair theorem. I see that I have 11 minutes left, so I think I'm going to be a little bit faster for this one. Right, so for the novel no-hair theorem, as I said, it was derived in order to close the loophole in the original work by Bekenstein, which didn't eliminate the possibility of hairy black holes for negative potentials. So in 1995, he derived the novel no-hair theorem, and in this case, he worked in a much more generalized theory. As you can see, this JKL are just generally covariant combinations of multiple scalar fields. Okay, I see now that I neglected to put the commas here. Everything here should be derivative, right? These are scalar fields. So there should be a comma mu everywhere. These are just kinetic terms of the scalar fields. And psi and chi are scalar fields. And one can have as many scalar fields as they want. So, but nothing else is assumed. The only thing that we assume here is the presence of n scalar fields that are combined in any generally covariant way. But one explicitly does assume minimal coupling to gravity. So strictly speaking, we have to have minimal coupling to gravity. So assuming that the horizon is regular and the positivity of the energy locally, he derives the following asymptotic behavior for the physical energy momentum tensor, Bekenstein. He proves that near the horizon, TRR has to be negative, and TRR prime, the derivative of the energy momentum tensor, has also to be negative. So I have shown just qualitatively, this is not an exact solution of anything. This is just a schematic qualitative shape that I made for you to get an idea of what the Bekenstein derived. So close to the horizon, TRR has to be negative and decreasing. And at infinity, TRR has to be positive and decreasing. These two asymptotic behaviors, meaning the behaviors that are in solid blue in my plot, these are not assumptions. These are consequences. These are possible to prove using the assumptions that I've written above in my slides. It is inevitable that this has to be like that in this very generic theory in Einstein gravity. So then the conclusion is that if we were to obtain hairy black hole solutions, in order to connect the two asymptotic limits, one has to have a behavior that looks something like the blue dashed line in my plot. It's necessary that it is like that. It has to have a minimum, it has to have a maximum, and it has to cross zero. So then, and only then, using for the first time the Einstein field equations, Bekenstein proved that this type of behavior is impossible. He essentially took a point right before the zero mark. He called that point A. He took a point right above the zero mark. He called it B, and he called the point of crossing from negative to positive point C. And he proved that this sequence of points are impossible to be realized if one enforces the Einstein field equations. And hence, he eliminated the possibility of ever joining the two asymptotic limits. And that is why in Einstein gravity, it is definitively impossible to have scalar hair with regular black hole horizon and so on and so forth. So the same authors in the paper I showed you at the beginning attempted to do the same type of derivation. So again, they followed in the footsteps of Bekenstein. So, and we did the similar process. We performed an expansion around the horizon. This is the expansion around the horizon. And let me remind you that this phi dot phi prime combination, I have rewritten it here, this appears in the regularity condition I showed you before. And as you can see, this f dot phi prime quantity is strictly negative in order to ensure regularity. So this fact combined with the form of TRR of the TRR expansion ensures that TRR in Gauss-Bonnet theory is strictly positive, which contrasts Bekenstein's work. Instead, regularity in his case demanded that TRR is negative instead. So that is one difference. The other difference lies in TRR prime in the horizon expansion. To make a long story short, everything in the first line is strictly negative, exactly the same as in the case of Bekenstein. However, in the second line, we have this quantity V, which is shorthand notation for this larger quantity that involves second derivatives. And this quantity V strictly can have either sign, which means the TRR prime for this theory is simply undetermined. There's no possible way to specify if it has to be positive or negative, unlike the case of Bekenstein. The expansions at infinity are exactly the same because the Gauss-Bonnet term is subdominant, so there's really no big surprise there. So let me summarize this table for our theory. The second line is exactly the same as Bekenstein. At infinity, TRR is positive and TRR prime is negative. However, near the horizon, TRR is positive, unlike Bekenstein, and at infinity is undetermined. And here is the big, the discrepancy that we have with the previous analysis in the literature. So this 2017 paper that I showed you before demanded not only that TRR prime is negative, but they demanded that this quantity V is positive, because they wanted to make this second term also negative. We are claiming that if we want to impose that TRR prime is negative, there's no reason for V to be positive. All we have to impose is that the whole quantity combined is negative. And then we have three possibilities depending on what we will demand for the sign of TRR prime. Either we demand that V is positive and TRR prime is negative, and that yields this blue parameter space. Either we relax their assumption, but still demand that TRR decays close to the horizon, and that opens the door for this green parameter space, or we simply assume that the sign of TRR can be anything close to the horizon without any restrictions. And then we also study the red parameter space in which TRR prime close to the horizon is in fact positive. That would mean that TRR is increasing close to the horizon. And this line, this blue solid line, is essentially this exact expansion in terms of the parameter beta defined before, and f dot dot. In a sense, this expansion, this is an exact Taylor expansion of the expression for TRR prime close to the horizon, and it depends on exclusively two parameters, which are phi dot and phi dot dot. We've simply traded phi dot for beta because beta ranges strictly between -1 and +1. And to make a long story short, this just summarizes what I already said, that we see no reason why TRR prime has to be restricted to be positive, negative, or anything in between. Instead, all parameter space should be open for exploration. And we did exactly that. We explored the parameter space, and we found counterexamples. We found examples for all three colors of the parameter space I showed you. And as you can see here, there's no problem showing here the results for the phi squared potential, for the phi squared coupling function. TRR can be positive. TRR has to be positive. That is enforced by regularity conditions. But then as far as the sign of TRR prime, there is no restriction. And we can have perfectly fine regular black hole solutions. So TRR can either be positive and decreasing, or it can be positive and increasing. And our numerics show that the novel no-here theorem is essentially always evaded, and there's no restrictions to it, and either sign is fine. Of course, we're not claiming this is true for all potentials, because we have only been able to show that for some potentials. It's possible for other potentials that this may not be the case. However, as far as general statements are concerned, we have shown a counterexample. We have demonstrated that TR prime can have either sign close to the horizon. Okay, I have reached the end of my presentation. I see I only have 1 minute left, so I'm going to keep this very, very short. Studying generalized theories of gravity is more relevant today than ever before, because we have recent discoveries regarding gravitational waves from black hole mergers, black hole imaging, gravitational lengthening, and so on, which allows us to probe the strong gravity regime, and that allows for constraining the various theories and the possible deviations and evasions of black hole no-here theorems. Gauss-Bonnet gravity is particularly promising because it's well defined and it yields rich phenomenology that is possible to constrain with experiments. As is well known, the theory admits Carey black hole solutions which are asymptotically flat for any coupling function. The exact parameter space over which the theory admits solutions, the only way we were able to constrain the scope of the solutions is through the old no-here theorem, and not without the novel no-here theorem, which is evaded trivially. There's many avenues for future work. As we briefly discussed, right? There's equivalent ways of defining the old no-here theorem. Why multiply by f like we did? Why not multiply by exponential to the f, as was pointed out as another possibility, right? Why not multiply by f dot? And all of this story should be clarified and expanded. We can also construct more realistic solutions and examine the evasion of no-here theorems for example, for the case of angular momentum, which in my belief will be more relevant for phenomenology as well. We can also take a more careful effective field theory approach and include more terms that are appropriate depending on the dimensionality that we consider. And we can apply the same methodology, of course, for other theories that are not of the Gauss-Bonnet type. And we're planning on addressing some of these issues in a future and longer publication. Thank you very much for paying attention to my presentation.
Okay, thank you for a good and nice seminar. Are there any questions or comments?
Actually, excuse me, I have a comment on one of the question.
Here?
I have so actually what mentioned about the no-here the old no-here theorems, right? With his papers. So could you go back to the slide with the old no-here theorem with the surface term?
Right.
Yes, here? Yes, here, yeah. So actually here we multiplied. Actually, we started with the Klein-Gordon equations and scalar field equation, not Klein-Gordon scalar field equations, and then multiplied by our coupling function f. But instead of multiplying f, the papers one indicated they multiplied exponential f. But whatever we multiplied in front of the scalar field equations, the surface term should be properly taken into account. They should not be dropped automatically. So that is the important part.
That's good. That's good. Yeah,
yeah,
some
okay.
of
Yeah,
the
yeah.
on the
Yeah.
was
Mhm.
already Kant's papers. They explained very shortly, but I guess that in your papers you clarify more detail about the.
No. Actually, what Kanti insisted, they neglected the surface terms, and then they only require in order to have a solution, f should be positive. That means automatically, then they say, f is negative, then the no-here theorem is a hold. So yes, actually, but it is not true, right?
I mean, in their papers they explained not exactly with the equation. They explained very shortly about the surface term in the state with the state method instead of the equation. And the other thing is that if you take the function exponential f, then you could extract the f. Then the integration, constraint integral integration does not have the form of the f. So you don't worry about the sign or the
yes, what we're pointing out is the whatever you multiply, actually what you should do is the integration by part. Then the surface term remains. So what you are saying is the surface term should be taken into account properly. We should not ignore them. They contribute very importantly.
And right, your analysis about the surface terms, whether or not that could be disappeared at the infinity or not, that analysis is good. Yeah. And the other thing is that the best thing is that to make the theorem, not the violation of the theorem. Actually, if you want to study the more in DGB theory, in the black hole in the DGB theory, then the best thing is to make the something extended Noether theorem, including the dilatonic Einstein Gauss-Bonnet theory. As you know, in Einstein Maxwell theory, there are 3 hairs, and here something is studied on the violation. But the best thing is to make the theorem with assumption. So in your presentation, if I'm sorry, in the first part of the your talk, I could not attend. I'm sorry about that. But in this case, the violation of assumption, when you make the theorem, people make the theorem, you should suppose, well, you should assume some assumption. Under those assumptions, you could make the theorem. The violation of the theorem in DGB theory actually violates some assumption. So violating assumption means that the violating of the theorem or does not applicable. The theorem does not applicable. So you could focus on that point. So
actually,
here
actually we didn't make any theorem or something. Actually, the initial study by Kantis and other papers, they made a wrong statement. They so in the old Noether theorem, they approached it in a wrong way by ignoring the surface term. So then later we found out we should not ignore the surface term, and that is very important role in the figure out to the whether one a hairy black hole exists.
I hope somebody make the extended Noether theorem, including the DGB theory. That is my hope.
Yes, you're right. I mean, in the sense that there is a theorem, in the sense that we are restricting the possibilities for black hole hair, our work does restrict the possibilities. The whole point is to restrict the parameter space, right? And our work takes into account the surface term consistently, and simultaneously it makes exact, concrete predictions for whether black holes will hairy black holes will exist or not, depending on the values of the parameters. So in that sense, for the old case, we can make a statement that limits the theory. For the novel Noether theorem, we were unable to do. However, the authors that we were discussing, they also claim to derive a theorem, but it was the wrong theorem. That's the point. They neglected the surface term, so it wasn't really the right approach. Yeah.
Okay. Sorry, small question. Like your conclusion about the Noether theorem, does it depend on the isometry of the black hole you take? Like you can also have some other kind of solutions, like the torus solution, or say black Saturn solutions, or something like that. So does your approach apply to that also?
We restricted ourselves as a first step to the spherically symmetric case, but indeed, following analogous argument, it is possible to study these other Noether theorems, I guess, that eliminates other solutions in the context of GR for other geometries. So our results are strictly for spherical symmetry, but following the same steps, one can indeed generalize this to other symmetries. And of course, the axis symmetry, the cylindrical symmetry is an important next step that we would like to make for sure.
Because my intuition is that their surface term calculation will be quite non-trivial in cylindrical symmetry or something like that.
I have no former experience with attempting to do that. I'm aware of the existence of no-hair theorems even for cylindrical symmetry, but I don't know how difficult or easy it is in that case.
Okay, thank you.
Thank you.
Yeah, thank you.
More questions?
Hi, I have also some question or comment.
All right.
Yeah, so scalar gravity has this always issue of frame dependence. And I guess you are focused on Einstein frame.
That's right.
Yeah.
Do you mean Einstein or Jordan frame?
Jordan frame,
like
yes, yeah. Because especially when you impose a regularity condition in methods, which frame you use.
Let me see. So this is the theory we work on. So it's my understanding that since there's no product between the scalar field and R, we're automatically in the Einstein.
Yes,
Einstein frame, right?
You worked on Einstein frame, yes.
Yeah, we work strictly.
Yeah, but the result can differ if you go to other frame.
That's right.
Jordan frame, yeah.
That's right. If we went to the Jordan frame, it's impossible for me to predict what would happen indeed.
But I guess you could do the parallel analysis, no?
I'm not sure how that is done in this case because I'm not aware of how to go from the Einstein to the Jordan frame backwards. I know how to go from the Jordan frame to the Einstein frame, but I'm not sure the backwards process, how one can do that. So
another comment, I have one comment. Actually, it's the result of Miok's another paper in collaboration with me. Actually, that the curvature singularity may not mean real physical singularity. Geodesic equation can be still regular and smooth, even though there is a curvature singularity. So this is a comment I want to make.
So you mean that?
I mean even though this Riemann curvature scale, this scalar curvature diverges, your geodesic can be complete there. Miyoung knows that example, yes.
Yes. Okay. Yeah.
Yeah. It's a bit orthogonal to your work.
Yes. I think we can try this analysis in the Jordan frame or Sting frames, but actually, there is no certain answers. The same result we can obtain. So yeah, but we can try and figure out that later, but we didn't do that at this moment.
Yeah, I'm not so sure that the Jordan frame would yield the same answer.
Yes, we should check. But
it's not clear. Yeah. Right. Any other questions?
Okay. Can I ask an elementary question?
Sure.
What is known about the stability of hairy black holes in your setup?
There's a lot of papers that have come out in recent years. It would be impossible for me to give you an exhaustive list of papers, but the bottom line is that it is coupling dependent. is my understanding. It really depends on the form of the coupling. If one has, depending on the sign of the coupling, one might get stable or non-stable, depending on the shape of the coupling. So I'm not aware of any general work that has happened for the stability, in the sense that they assume some arbitrary coupling. I have seen papers with coupling specific results, and yeah, the answer is that whether the perturbations are stable or not depends on the coupling exactly. That's my understanding.
Sorry, one small comment, like Hartog and collaborator had this paper in which they were analyzing this no-hair theorem in with some positive, I forgot it, like positive mass dimension or something like that, right? Was Hartog and company, I think, early 2015. So, like positivity of the mass dimension or positivity of mass. Just look at.
So
Oh, sorry, I forgot it actually.
okay,
Sorry.
no problem.
Yes.
I would like to, yeah, one more question.
All right.
Yeah. Do you have any intuition about the Gauss-Bonnet terms in terms of force in your setup? I mean, it seems to me that Gauss-Bonnet term in your setup implies a kind of repulsive force near the horizon. Is it right or not? Yeah, my naive expectation comes from your TRR, sign of the TRR component.
I'm not sure.
The part is the check the T energy momentum tensor TT part minus rho. So Sangon is right. So in the near horizon limit, there is something non-positive energy density. That is just violation of the assumption in the Noether theorem. In this setup, if you obtain the black hole solution, and you could check the energy momentum tensor part. So TT part, the energy momentum tensor, as you know, indicate the density of the hair, scalar hair, the near horizon limit. There is a negative region of the energy density. That is exactly violation of the assumption in the theorem. So solution violate assumption, which means that the theorem could be violated easily.
That's right.
Actually, I have also comment. If you expand the matrix near the infinity, then the for example, GTT component is expanded, 1 minus m over r, and then the plus sign later. So actually, the 1 over third, 1 over r to the third, there is a contribution of the dilaton field, and then as I remember, the sign would be positive. So it's like, if you consider Reissner-Norsener black holes, its metric is like 1 over 2m over r plus q square over r squares. So then in that case, meta field, or the make a contribution positively, which is the repulsive force near the black holes. So I think in the dilaton case, it's also this meta field plays the same rules like the electromagnetic field.
Yeah, right. I'm sorry. That is about the TRR part. Yeah, is right. Yeah. Sorry. Sorry. I'm sorry. I'm mistake. Mio.
This, yeah.
In the near horizon limit, so density is negative. That is right. Density, the density of the scalar field, outside the horizon, near the horizon region, the density has a negative sign, and if the R is larger, then the density has the positive. So that is the violation of the assumption in the Bekenstein's Noether theorem. As you know, in the Bekenstein's Noether theorem, he made some assumption. One of the assumption is non-negative energy density in everywhere. That is one of assumption. In Einstein's scalar theory, here theory is violated, and the configuration of the energy movement tensor, the configuration of energy density is violated. So some of assumptions are violated to make the composite of the to make the theorem. So theorem could be violated easily.
Yes, that's right, and that's the conclusion we also made, that it's simply violated. As you say, the positivity of the energy is violated. Also, the non-minimal coupling is violated. Bekenstein strictly assumed minimal coupling. We have non-minimal coupling, and the Einstein field equations are completely different. So one wouldn't be able to use that argument that there cannot be any crossing from negative to positive of the energy momentum tensor. The point is that we follow the steps one after the other and see if we can derive a new novel Noether theorem. And we see that it's impossible. And for this reason, it is simply evaded. But the paper that I cited before, and we claimed we have a discrepancy with respect to them, they're not making the same claim. They're claiming that you need to impose specific conditions for the novel Noether theorem to be violated, which is not correct. But what you're saying is absolutely true. The positivity of the energy is strictly violated in this case because TRR is positive close to the horizon.
Okay. Can I ask one more question?
Sure.
Okay. So, I mean, to summarize your result in a simple sentence, so, I mean, what's the condition for F for the held solution existence? So, beta, I mean, the inequality for beta square, something like that? No, I mean, F prime, I mean.
We were unable to find a simple condition that is only a function of some of the coupling itself. The only thing, the best thing that we can state is that the only restriction that we're able to find is the case in which simultaneously the surface term, meaning this quantity, vanishes. If this quantity vanishes, then only F greater than 0 is acceptable. That is the final conclusion we made. But of course, one cannot ensure that what this is. One cannot know whether this is 0 or not unless one evaluates, solves the equations of motion, find what is phi infinity, phi 1, and so on. But yes, if the summary that you're looking for is if the surface term vanishes, meaning if this quantity vanishes, then only positive F is allowed. If this surface term is non-zero, then there's no restriction and any F is fine. Sorry, my mouse is very sensitive and I sometimes skip a page or two. My apologies.
But still, so in all your argument, F prime, no, F dot square is smaller than something, some quantity is required.
That's right. That's right.
Okay, so within that condition, you need another condition for the paired solution. I mean, the asymptotic condition, something like that.
Yeah, I'm not sure that I understood exactly what you mean. Do you mean you can re-express what we're saying in a different way, or?
No, I mean, so in the equation 18, you said there's a condition for the solution existence, but in this argument, still you always assuming the f dot square should be smaller than some quantity. That's I mean the basic assumption.
Yes, yes.
Okay,
Actually, we need the condition to have the regular black hole solutions.
Oh, I see. So
Yeah.
Yes, where is it? It's here. This one. Yeah.
Yes.
Okay. Yeah. This one has to be satisfied.
And then the
Or
next
this
thing-
one.
Oh, yes, right.
yeah,
Sorry.
yeah.
I forgot. I wrote that. Yes. Okay.
I see. So you need both condition at the horizon and at the infinity to have a regular. I mean, to have a regular paired solution.
Yes,
Indeed,
basically,
indeed.
and at the horizon. Yes.
Thank you.
Okay, it seems that there is no more question. We would like to thank speaker again.
Thank you for the invitation.
네. 제가 여기 그 교수님들 계시니까 질문 하나 하고 sorry Alex, I will ask some questions to the professors, expertise on the gravities. So actually it is related to the question about Jang-Hyuk's. Actually what I'm not sure is this is the black hole solutions, but if we make the change those black hole solutions, if we change the frame from Einstein to Jordan to Einstein, so it is always the case black hole the black hole in the Einstein frame becomes the black holes in the Jordan frame.
I mean, at least the spherical symmetry is preserved, yeah?
Yes.
And
yes,
I
yes.
know the example where depending on the frame, the singularity can be removed from the metric.
Yes, but what I'm saying is not singularity about the black hole solution itself. In the Einstein frame, it would be the black hole solutions. In the Jordan frame, could not be the black hole solutions. I'm just wondering that can happen.
So your definition of black hole requires horizon? Or?
Yes, right. Yeah, yes, of course, yes. Existence of the horizon.
So that horizon can be converted to a naked singularity, depending on a frame.
Okay.
At least this is the case with the four-dimensional, Mathless scalar.
Okay. Thank you.
Okay. 미역.
네.
I mean, our paper
네.
has
Yes.
exactly that four-dimensional scalar scalar gravity solution as a one example out of three examples. Yeah, I think that example is also relevant, but
all our example was the black hole solution, one frame, and the other frame is also the black hole solution, right?
I have in my mind over my second comment that even though it's a curvature divergence,
yes,
can be physically geodesic can be complete.
Yes. I mean, okay, that point. Yeah, I know about. Yeah.
I know this is not your consideration in this work, but
yes,
I wanted to remind you.
Okay, thank you. Yeah.
Leo?
Yes.
Yeah. Regarding the solution, so you design, by choosing some particular potential, is there some exact solution? Have you searched it in the literature?
Actually, I didn't see any. Yeah. I didn't see any, but actually the one solution was the I think Alex found. I'm not sure. Okay, sorry, I'm a little bit confused. Yeah, so Yeah, actually, it wasn't a Gauss-Bonnet terms, but it was the massive scalar field employed, and then they found analytical solutions, but the field itself, scalar field itself, was singular at the horizon. So yeah, it's a black holes, but for example, this path phi was singular at the black hole horizon, so it's not the regular black hole solutions. But there was analytic solutions like that.
And regarding the inner horizon.
Sorry?
Regarding the inner horizon.
Inner horizon. Yeah, actually, we don't know the existence of the inner horizons. Yeah, so please give any
but I
any comments.
suspect that I mean, at the inner horizon, if it exists, scalar field is diverse. So I mean, it is not regular there. Because recently there's a so-called no scalar hair Cauchy horizon theorem, something like that. So yeah, so if I consider in that way, that's my suspicion.
Okay, yeah.
So I think it is interesting. I mean, subject. I mean,
yeah. Okay. Yeah. Sure. Yeah. Actually, we didn't know that, so we'll take a look. So could you give us the reference you mentioned?
Yeah. Okay. I will let you know.
Yeah. Okay. Thank you.
Alex, thanks for nice, interesting talk.
Sorry,
thanks for interesting talk.
Thank you for offering to give the chance to do this.